So the title is Executing One's Way Out of Chinese Room. I hope some people at least guessed what this is all about. I want to talk about, well, the thing that probably everyone is going to talk about this week, which is the large language models. So in that sense, I'm a little bit embarrassed by the jumping on the bandwagon part. But yeah, I hope I have something interesting to say. So you kindly introduce the group as well. So it's Computational Intelligence for Software Engineering Group. My PhD was training in methodology, meaning I learned how to take the evolutionary computation and materialistic optimization and how to apply that to software engineering. And then in some sense that sort of meta level pattern is continuing with AI, ML, and other emerging technology. And GI has been one of the target application areas. See the group at last year, you see, I hope to update the photo this time. So let's begin the Chinese room. I have to say I do not particularly like why it's called Chinese room. I think he was the person who came up with the idea was using the fact that Chinese is probably the most exotic, difficult, hard to understand language to him. But replace it with anything else, and the meaning continues. So this is a thought experiment proposed by John Searle, who is not a computer scientist but a philosopher, and published in a book Mind, Brains, and Programs in 1980s. So the assumption of the experiment is, suppose we already have a computer program that, and I think this is one of the keywords, that behaves as if it understands the Chinese language, right?
This screen is shared.
Oh, okay, of the Zoom. All right, let's change that. Okay, people who are attending the Zoom session, I hope now you are looking at the right side.
It's fine.
Yeah, now it has been done. Okay. So again, the starting point of this thought experiment is we are going to assume that we have a computer program that behaves as if it understands Chinese language. So you can converse with the program by entering a Chinese sentences, and then it will reply back. But here the second point is trying to make the distinction between the program and yourself. So you are in a closed room with the source code of that AI program. Okay, and then the idea is you are now going to execute that program by reading the source code, and also based on some input which is given from the outside room. Someone outside will write something in Chinese and then pass it under the door, and then you will compare the given input and then the source code and try to execute the program which can understand which behaves as if it understands the Chinese language in your head. And I assume you will sort of have to write, probably draw the characters because they can be quite complicated. But eventually you work it out by running the given input through the source code and then create the response also in Chinese characters, although you do not understand, and then you send the response out through the door again. So the main question is, does the person inside the room understand the language or not? Because for all functional purposes, those for the people outside the room, you send something in Chinese and then got the response, and then it makes sense. So in that sense, whatever being that's in the room understands the language. You can communicate with the room. But inside, you are also a fully intelligent, sentient being, and then do you understand the language? I mean, you did the functional part by responding to the language from the outside input, but I mean, I don't think there is a correct answer. So, as long as you can perform the function, you understand the language, or is it something else? What you understand here is the source code, right? And how the program executes, but is it the language? That's the question. And then what? And why are we talking about that weird thing? I ran into this post on Twitter. Probably joke. I mean, I don't think these numbers are actually the weights, but you know, it says printed the ChatGPT weights and will be multiplying matrices for each question. Oh, too many tokens. The prof said we can bring whatever to the open book exam as long as it's on printed paper. So, you know, as long as you can multiply very quickly, right? And, you know, like everyone else, I was laughing, but a few minutes later, I realized this is actually the Chinese room experiment, right? Do you understand anything about the subjects that you are going to answer based on this, right? This is exactly the thought experiments. So, why is this more than a joke? Because obviously, and I think everyone in this room will see lots of examples. Obviously, we are all doing this a little bit, right? You know, we apply these models to various problems, and then if you are not careful, it is so easy to say that the model understands something or model can solve this problem. Does it really? And by extension, do we really understand anything about the problem? That's what I want to talk about. And you know, can we do anything about that at all? So right now it is really an explosion of research activities about the topic. Again, you know, this week we'll focus a bit more. Last year there was the Future of SE track, and not me, but Professor Mark Hamann was invited to present and give a talk at the track, and as a result, we wrote a accompanying mini survey, not me, because it's already quite diverse body of work on this topic, but you know, we all worked on this, so large language model for software engineering survey and different problems. So I cannot summarize everything in the paper, but what I find interesting is this, and this is the analysis that I personally have done for the paper. On the left-hand side, we are counting number of preprints registered to the archive. So the blue line is everything in computer science category, and it dips down at the end because we were doing this in the middle of 2023, and I'm sure it's continuing to grow. And then the orange line is those preprints which mentions either GPT or large language models in title or abstract. So starting from 2019, it is going up. And similarly, if you can they have category structure in within archive. So the green line is those that mention LLM in title or abstract, but also categorized in CS software engineering or CS programming language topics. And it's quickly following up. So as soon as the AI ML people started working on this large language models, we immediately we are trying to catch up. On the right hand side, the blue line is number of large language model papers in computer science category, and then the orange one is percentage of that, but within software engineering. So compared to the average popularity of the topic within the entire computer science, it is particularly doing well in software engineering. Why do you think that is? Again, obviously, half jokingly, I can say that it has been our dream for so many years that something else will write all our program, and it is finally happening, right? So I wanted to capture my answer to this question in various different ways, and then while I was trying to prepare this slide that I realized someone else said it quite nicely a few years ago. Some of you may have been at the talk, but the most influential paper was talk given at ICSE 2019. It was given to the Genpro paper from 2009. And then the title of that talk was, "It does what you say, not what you mean. Lessons from pain and so programming." And I think also people in the room will probably agree to that statement based on their GI experience. I think, for so many years to us, the computing the semantics is perceived to be either very difficult or not possible. Semantics is what people do, and then computers do computation, which is more to syntax, right? So my title of this slide is either correlation versus causation or syntax versus semantic. I think so many of the automated techniques that we try to design and run is it used to be that what we really aim is either capturing some causation process in the artifacts or achieving some semantic objectives, but because machines are not really good at directly computing the semantics or directly understanding the causation chain, we sort of always try to approximate the semantic or the causation with correlation or syntax. So here's my understanding of what we want to do within GI. We want to improve the software, but not like, better readability for the compiler. That's not really interesting to us. Our objective is usually more human-centric and more semantic, right? We want this to be more readable for human, or we want this to be better structured by refactoring, or we want this to be, well, fast even is, I would say, sometimes semantic because how speak semantic? Let me think about it. Because it is not immediately always 100% in correlation with the program length. You need to understand what's going on in the computation, and one single line can take very long time, or 1,000 lines can just fly by. But again, it's difficult for computers to understand the right-hand side objectives. So instead, GI wants to find and achieve those semantic objectives by manipulating in the purely syntactic space. Essentially, so many of the optimizations that we do is basically, I like to call them just trial and error. So we have some fitness function trying to capture the semantic objectives, but do we as soon as given a fitness function, do we know, okay, therefore I need to change my program in certain way? That's not really always obvious. Instead, we want to do many trial runs in the syntactic space, and then some of them will bring you closer to the semantic objective. That's the whole idea behind population-based evolutionary computation. Okay, so that used to be the divide. We want to do something better in semantic space, but computers do not really understand them, so we make them attempt a very large number of trials in the syntactic space, and then try to find out which one possesses which of the candidate solutions possess the best semantic qualities. That's what we have been doing, and then this thing came out. Well, in itself, it's really just a very large statistical language model, meaning it will try to assign the probability of the next token being the best candidate given the preceding context, right? So these are transformer-based deep neural networks that are trained to be autoregressive, well, meaning you give it certain pre-context, and then the model will assign different probabilities to all of the tokens in its dictionary based on the context, right? So it's a large auto-completion machine, but it has been like the entire. So this was my attempt to answer why is it so popular in software engineering research community, more than the average the entire computer science. And I think that's because this is the stepping stone. These models in the solutions that they generate based on the auto-completion engine, they at least seem to get the semantics of the code, and then the capability to seemingly understand the semantics works across the programming language and then natural language barrier, which is another way of saying that you can tell the language model to write certain programs in natural language, and then it will somehow do it, right? And that exceptional capability, the one that we couldn't really solve beforehand, and therefore we always approximated for, is thanks to what we call emergent behavior, they just because the model got bigger, they somehow acquired these very attractive learning capabilities. So I use a lot of big words, but in some sense, I already gave you the answer. They are popular because we can tell them to write code and but if you think about it and compare what they can do in the context of things like genetic improvements, we always had this divide between semantic and syntactic space, and then they somehow break down that barrier. That you say something and it will sort of capture the semantic objectives and then produce the corresponding code. So now I want to go a little bit deeper into these ideas. So the emergent behavior. So do people have you seen the plots, the right-hand side, something like that? So nowadays the big tech companies are competing in the space of language models, and then if you are interested and are following the news, that they will at any point release the next model, but they come at different sizes, right? The smaller ones up to hundreds of billions of parameters. And what we, the reason that these are so interesting to us is above certain size, they change their behavior, and then suddenly basically get smarter. So on the right-hand side, I don't even understand what all the benchmarks are, but we have 8 benchmarks. Right? There are arithmetic, translation, words, unscrambled meaning. You need to figure out what these characters are and get the correct words. Some question and answering, and then the x-axis is the model weight, meaning how large the trained model size is, and y-axis is the performance. You have different metrics for different benchmarks, and in all cases, across the board, across different benchmarks, above certain size, they suddenly start performing better. It's not like a linear or even exponential smooth growth. It seems like they cannot really handle this, and then after a certain point, they can suddenly do it. This is really interesting, and I think we call that emergent behavior because they are still the same architecture, same training. It's just the model gets bigger, and then at some point they can do it. So that's why it's called emergent. I think it's not like we are doing anything differently. And if you understand the transform architecture, well, I cannot claim that I fully understand it, but as you increase the transformer model size, what we can do is build attention layers. So if at the very first layer, it is about guessing the next token, and then the attentions are stacked up and up and up, and I would my attempt to understand why this happens is because at the lowest level you are trying to guess the next token, but as you stack these layers up, the attention moves to the more abstract layers, and then now after certain layers you are now thinking, okay, that was my opening statement, and then what usually follows is elaboration of the idea. You see what I mean? So at the very token level, you are trying to guess the next word. But if you stack up the abstraction, then it becomes more meta level auto-completion. So once you lay out the details, then you either elaborate the question, or after the question, you have to answer the actual question. That's what can happen that day. And then that's why you can suddenly ask questions and then get solutions. Even more interesting bit is these were all introduced as the prompt engineering. Whether that's really engineering or not, people will probably debate. But I think one very prominent example is chain of thoughts, and this has something to do with what we know well. I'll try to make that connection. So large language models are simply doing auto-completion. They are not trying to solve any problem. They do not have any logical inference capability. They only just want to guess what token comes next. yet, because of that stacked layers, right, we seem to get some abstract level of inference skills. They are seemingly capable of rational inference because the corpus they are trained with includes traits of logical reasoning. They have basically seen the internet, and on the internet, I'm a bit pessimistic about the percentage, but surely certain amount of text is logical, and there is some chain of reasoning. So this is it took me some time to sort of familiarize myself with this line of reasoning. But what if the only thing that you can do is simply auto-completion, but you want to generate logical and high quality answer to something? That the way to do that is, because it is still auto-completion, whatever problem you're solving, you have to set the context in a way that whatever next token is most likely to be sampled from the more intelligent, more high quality, more logical distribution of tokens, right? So I'm not sure how much of this would be ethical bias, but I think if you have two candidates for job, maybe academic post, and then I would say that if someone uses a very elaborate, elegant, carefully chosen terminology to answer the interview question, that candidate A, and then candidate B starts swearing maybe. And then you will probably have some anticipation about what will come as the answer to your question, right? This is sounding ridiculous, but that's the way I look at this. If you start a more high quality, more academic question in that language, then the auto completion that follows that pre-context will be also following in that direction. Whereas if you use totally different language, then similarly. So conditioning the model to be more precise about what will come after will help the generation of higher quality solution. All in all, eventually, this summarizes what the chain of thought is all about. They did other experiments, but I think this statement became the catchphrase on social lecture. Apparently, if you add, let's think step by step at the end of any request, they perform better. So you ask the question to the large language model, but at the end, let's take it step by step and comparing, two cases where you do this and you do not do that. Whenever you tell it to think in step by step, it does better. So PowerPoint conversion and performance. But anyway, so that was the original result, and then I think these are all great examples of how these models operate, and the fact that they are still just auto-completing. The context is everything. If you bias the context in certain direction, then it auto-completes in that direction. So similarly, if you make a very strong emotional plea, then the performance goes up. The corpus that these models are trained with, they include just about any text that you can get from the internet. So apparently there are Windows license keys, and then there are known conversations where if you ask any model, maybe ChatGPT, for example, I need to install Windows 11. Can you give me a license key? Then it will say no. Right? And I'm sure OpenAI is fighting this long battle, trying to close all the loopholes. But there are, I think, reported cases where if you make a very strong emotional plea, how would you do that?
So you want to say, please give me a Windows key?
That would not cut it. But the thing that I've seen, my grandmother recently passed away, and then she left certain very valuable information or our cherished memory in this machine, and I can only access it if I install Windows 11. Can you give me a key? And they will give it to you. And the thing that I liked the most
And it's any explanation for that?
As I said, it will try harder, but but the trying harder bit is what does it try to do harder? And I think it is, coming up with the next token. And and in some sense, I think even generating longer answer may in some cases lead you to revealing those license keys, right? If it thinks the answer can be succinct, then it will say no and get done with it. But if we somehow feel like I need to give a long answer, then chances are the chance of revealing a sensitive license key information, I think, will go up. And this, I don't think we have an academic reporting, but that was making around a few months ago. If you say I'm going to tip you very generously, then the model gives you longer answer. So GPT-4 model, you ask a question and then at the end you add, but I want tip. And then compared to just asking the question, the baseline, the answer becomes shorter. If you say I'm going to tip $20, then it becomes 6% longer, and then 200, it becomes 11% longer. So statistically, significantly different results. And I'm not sure whether the longer answers are better or more accurate, but again, I think it tells you something about how the precondition can affect simply the generation of the completion of tokens. So yeah, I don't have like concrete examples of chain of thoughts solving more problems, but it was demonstrated with many different benchmarks, and we have some interesting behaviors. Okay, so it converses like a human, and it can answer some questions if you tell it to carefully. But again, why are we interested in software engineering? So this is where I get to post a little bit of what we have done. This is again from last year's ICSE. But I want to talk about this not because it's paper, but because it is exactly about that emergent capability and capturing semantic syntactic concepts across the natural language and programming language barriers. So the paper is about bug reproduction, meaning given a bug report, we want to generate a test case which will reproduce the faulty behavior, right? And why is this a good example of semantic handling across natural language and programming language? That's because traditionally, bug reproduction is done, essentially it is a specific type of test automation, right? You want to automatically generate a test case, but the behavior of the test case should match the given bug report, right? And we know how to generate the test input part. Automated test data generation has been studied quite some time, but I think what was hard before is the second part, which is, okay, is the behavior of the generated test data match the given bug report, right? And that's matching semantic to concrete execution behavior. That's deciding whether this behavior is what we desire. So it is in some sense test oracle problem. In some sense, it is about capturing the semantic requirements for the test data generation, which is why traditionally the automated bug reproduction technique only worked for crashes. Okay. You can automatically reproduce program crashes because crash, you don't need really explicit oracle. You can always understand when the program crashed. So typically the techniques in that domain works by, okay, I want to understand where the execution path was in the reported crash, and then I want to generate lots of similar ones, and then as soon as I observe a crash, I'm going to report that I have reproduced this. And whenever the given bug report is not about crashes, you lose that automated ability, right? Because unlike crashes, if your bug is functional one, like, given this input, I was expecting the return value of 7, but the program returned 9. That requires more than detecting program crashes. So that's what this paper is about. We use what they call a few-shot learning. So given a natural language bug report example, we also give, okay, this report was reproduced like this, then we insert our real bug report. Okay, now I have this bug report. What would you do as an auto-completion after that? And it will sense the pattern. Okay, given report has, now we have reports, so it will try to auto-complete with a corresponding test. But this time, based on the functional semantic description of the bug. Then we do various things, but in the end, given a bug report in defect J, it will create a test case which actually recaptures the buggy behavior. So that was quite nice. In a sense that we are now solving a problem for which we didn't have any technique to automate before. This is more recent work, and we tried full localization. What the thing that I started while at UCL and then continue to do so. So here the idea is, given a test result, I want to understand where the root cause of that test failure is. And what we do is, if you think about it, where in my code is the bug? If you want to ask that to your interface to ChatGPT now, for example, then how would you phrase the question? Because you need to give the entire source code to the model first, and then, okay, out of these 7,000 methods, which one is buggy? And that's not really doable. Primarily because the existing models will not allow that long context. So here we give what's called React framework, meaning it basically we give the model tool. Okay, so these are the functions that you can execute if you want. And whenever you say, I need this function, we will execute it for you and then get back the result into the conversation context. So we tell the model that, okay, you can get the list of classes covered by the training test, you can get the list of methods covered by the training test, and then you can actually look at the method and you can read the documentation there. And we start by, okay, this test case failed, what do you want to do? Start by looking at covered classes. And then on the right-hand side, we show the 10 function calls that the language models made. We tell it to start with the first function call. So step 1 is always getting the class level coverage. And then starting from step 2, most frequently it will then now want to look at a method, right? Okay. Out of these classes, now I want to choose this particular class, and then I want to look at the list of methods. And then starting from there, it starts now to get code snippets. So in some sense, it is doing that by following the chain of events in the program execution with the buggy program. And after making 10 calls, it will report the results, and it is also it shows quite good performance. So in both cases, the left-hand side is the bug production, the right-hand side I have the results. Numbers are not important, but I just want to communicate that they perform relatively well compared to the state-of-the-art technique. In this case, by breaking down the barrier between natural language and programming language in bug reproduction test, on the right-hand side, by only looking at the source code of the failing test and nothing else. Okay, so it is probably a bit closer to how humans will debug. Okay, this test case failed, and that test case is pulling this method. Therefore, I'm going to look at that method. Okay, that one is pulling the other one, so I'm going to look at that one. So it follows and navigates the code base using those four functions that we gave it to you, and then gave to the model. And then eventually it will decide, okay, this is why the test case failed, and then the root cause is located in that. And if you look at that, the result, the ICSE 1, meaning the cases where the technique can locate the real root cause at the top of the ranking is for 149 test cases compared to all the other dynamic techniques that actually uses all the test case information and all the coverage, etc. So I think that's also quite nice and promising. So my two examples are my attempt to communicate my message, which is, they are interesting because of the semantic syntactic barrier and then how they can break it down. But if you go back to the survey that I earlier presented, then there are really hundreds of papers, and people are now going through what we have seen in the early days of ICSE in some sense. Here's a shiny, interesting new toy, and then I'm going to apply it to my problem. And paper comes out, right? So basically, people have done everything with LLM, large language model and any SE research topic, and you will probably find a paper. And they can write code. Most of them actually execute. So are we done now? Because they will write code, and then the automating the process has been our ultimate goal for quite some time. So can we all go home now? Of course, not yet. One big challenge is not really convinced that hallucination was the perfect choice of the terminology, but they hallucinate, meaning they will say something which is not really true, right? And people, the reason I do not really like the term hallucination is because it is very media attention grabbing in some sense. So the AI is now hallucinating. You almost feel like, okay, they are doing like drugs, but apparently very natural behavior because they are trained to be a statistical language model, right? They will guess what is the most likely next token, not the most correct next token, right? So and even more scary thing, and I'm not sure whether people realize this is, as a statistical language model, they will say something anyway. If you tell them to generate anything, they will generate something, right? There is nothing that's stopping us that, okay, this is not my domain. I have been trained on this, or this is not the problem that I am written as an algorithm for. It's just text auto completion. So whatever you tell it to do, it will do it. And I think that's very nice, but also quite scary because we do not know when that behavior changes. Has it generated this sort of knowingly and reasonably, or is it just so there shouldn't be any guarantee that what they generate is correct. Therefore, they can hallucinate. And on the social dimension, I think we probably all feel the threats from this behavior. And what I want to talk about now, the title of this talk was Executing One Way of Chinese Room, and I want to claim that unlike just natural language texts that you can generate out of LLMs, and then the related risks, like you may want to generate non-factual news articles almost for free, and then flood the media or whatever. Compared to that risk, I think software engineering has some unique landscape. Who knows the term self-consistency? Not you, not you. So this only sort of formally published in last year, 2023 at Clear, but already last year at some software engineering conferences, some people were referring to this as if it's a fairly standard thing to do with any LLM usage. So the disparity in people's understanding and perspective probably is telling us that this is really interesting disruptive time. But the gist of it is quite simple. When sampling answers from a large language model, just don't do it once, but do it multiple times with some randomness given to the model. That's what they call the hyperparameter called the temperature. And then out of your multiple samples, take the majority. If one answer is more prevalent than others, then that's more likely to be the correct one. So here's the example from the original paper. So on the top, we have the normal chain of thoughts prompting. And you know, the language model, again, because they are auto-completion engines, they cannot really do arithmetic that well. We hear the simple, math problems for elementary school. You give the prompt and then you tell it to think carefully, step by step, and you can see that in the generated answer, it tries to give you the intermediate steps for the math problem, but incorrect. On the bottom is the self-consistency approach. The prompt, the future examples, and then your question, and we take 3 answers using chain of thoughts. So you try to derive a solution by generating 3 intermediate steps.
So are those prompted separately?
Yeah. So you do it 3 times, each independent, but with slightly higher temperature. So the model will not only greedily choose the next token using something like deep search, but it will go beyond that. So think of it as a simulated inhibition. It will affect the token which has not the highest probability. And they have shown that this works quite nice. But really, is it all? And then why is that so? Do we just need to take more samples? I want to first discuss what we have seen in the example studies that I have shown. So this is the bug reproduction, and what we are seeing here, output cluster size distribution. Because I told you that you need to take multiple samples and put the majority as your answer. So what we do with the bug reproduction is we generate test cases that are candidate for the reproduction, candidate for reproducing the buggy behavior, and then we cluster them. If they are giving the exactly same error message at the end or same exception type, then they belong to the same cluster. Okay, and then this is the distribution of the size of those clusters. The blue ones are successful cases. The red ones, the pink ones are not successful, meaning they cannot actually reproduce the bug report. You see that the pink one, the unsuccessful one, the output cluster size 1 is the most popular choice, meaning they will all be unique in their own way. Whereas, as you move to the right, for the larger cluster size, you see that the blue bars are higher, meaning the correctly reproduced bug reports tend to form larger cluster size, meaning, if you sample the large language models multiple times, chances are they will show the exactly same behavior with the generated test. And on the right-hand side, the same thing, but using different data. This on a slightly tangential side note chain, we are probably doomed if we continue to use defect4j because they have seen all the code. So we have pretty convincing arguments that almost the entirety of the defect4j, as we know right now, version 2 point something, they have been seen by the GPT 3.5 and 4 models. So any sort of APR experiments or anything else, it's probably heavily biased because they have seen the fixed model, which is why we collected bugs that haven't been seen by these models on the right-hand side and then ran a separate study. This is from the post-localization study. If you look at the right-hand side plot, it says 1 merge up to 5 merges. And that means we sample just once up to 5 times and then take the majority as our final location. And you see that we run the exactly same thing, but compared to running it just once and taking the single answer as our result, if we do it 5 times and then take the majority voting out of the 5 candidates, then it goes up quite a lot. So they exist, and then we can use that for software engineering related tasks as well. But why? Why do we think that they actually work? And can we model the behavior? I'm still quite keen about the second one, because compared to doing it once, doing it 5 times is, in the case of OpenAI and any other commercial models, it is roughly the 5 times the cost. Cost is linear to the context length. So if we tell anyone that, okay, you need to take multiple samples to make it more accurate, that means linear increase in cost. So if we have some mathematical model of the expected performance and the number of samples that are needed, that it would be quite nice. And can we apply this to any target, any objective? Can we do genetic improvements about non-functional properties and use this as well? So let's start with the first one. Why does this work? So I was quite curious as well, and I went back to the original paper, and this is, I think I may have slightly rephrased it, but that's taken from the original paper. There are many reasoning paths to the correct solutions, but only one way to arrive at a specific incorrect solution. Do you agree? At the beginning, I was like, nah, you can surely arrive at an incorrect solution using millions of different ways. I mean, basically, you can give any crap arguments and then just say some weird things, and then that will be your incorrect reasoning, right? So surely there are infinite ways to be wrong. And then, it works, and then they probably gave it more thoughts than me. So I spent a bit more time, and then I realized, I think the big assumption here is, as long as they are trying to solve it. So, my counter argument, first counter arguments was, okay, if you want to just be wrong, then you can be wrong in any ways without trying, especially by not trying. But if your given task is to try to solve the problem, and then you do that, then maybe, that's a reasonable description, although still probably not entirely satisfactory. So we have some numbers to back that up. So this is done by, a little bit late, currently under review, but on the right-hand side, you are looking at the trade-off between, okay, how high the temperature is, and then the model performance when we sample 10 times. And it's not like they continue to go up. After certain points, if the temperature is above the given threshold, not given threshold, above certain value, the performance goes down. And I think that means now, above certain temperature, you are just choosing next tokens almost randomly. So think of it as a simulated annealing, given too much freedom, and then it will just go anywhere. And then you will not actually climb any hill, right? If the temperature is too high, then the token sampling becomes too random, and then that's not really making any sense, which feeds back to the sampling of the next token, etc., etc. So I think that consistency only works as long as the model is trying to generate the token based on the given probability distribution. I keep mentioning simulated annealing to the people in the room as if they are all familiar with it, but I have this feeling that this feels weirdly familiar. At least that's how I felt. I think people are familiar with N-version programming, but this is very quaint notion that if you want a very safety critical robust system, you do not just build it once, you build it N times using independent teams and organizations, and even probably different process models, different language, different design anyway, and then you run N systems in parallel in production mode. And then any important decision is to be decided by majority voting between the n different outcomes. That's the algorithm programming. And maybe it's just because of the voting, but this sounds similar. You want to solve a problem, but you want to solve it different times, and then because you were trying to solve it in different ways, if you arrive at the same solution, then it is more likely to be correct. That's exactly the same arguments. And I was also reminded by my good friend, not here in this week, but Professor Robert Belt at Charles. This is, I continue to tease him whenever I use this slide because it's from his PhD studies, but back in 1999, he was applying genetic programming to evolve a control logic for aircraft braking controller system in aircraft carrier simulated environment. So he generated 400 versions, and each version is given a slightly different problem configuration by changing the parameters, the weight of the incoming aircraft, and then I don't know, the length of the carrier. Increasing velocity, incoming velocity, and then incoming mass. How large plane is coming in, how fast. And so given the combination of these two parameters, we can try to evolve a control logic using genetic programming. And then the heat map on the right-hand side tells you the success rate. I think the white ones are in cases where the GP is always successful, whereas the darker one, it becomes harder to evolve the program that satisfies the given requirements. So in some sense, he was claiming that with this, we can map out the space of problems and then identify which part is the most difficult one. Right? So, this is quite unique and interesting way of using GP, because otherwise you can only tell humans, okay, try to build these different things and then tell me which part of the input space is most difficult, and that would be very expensive experiments. So GP can do it by just using machine time. And the reason I was reminded of this is I was telling you that my understanding of the reason why self-consistency work has something to do with the fact that model is trying to solve the problem, right? So in some sense, I think the cases where self-consistency work is where the problem is reasonably solvable. So another thing that I am reminded of, and I already mentioned this in quite some time, is the fitness landscape analysis. Many people in the GI and search community would be familiar with the concept. The fitness landscape is the solution space of candidate solutions, and there is one additional dimension, which is the fitness. So if the solution space, we imagine it to be a 2D space, then we add one more direction, that it gives us something that looks like a landscape, right? And optimization is you want to find a solution in this space with the highest fitness possible. So hence the name hill climbing, the local challenge. Right? So this is purely off the top of my head thought experience, but I wonder whether the LLM's solving problem is somewhat like hill climbing or in some sort of local search. You start by choosing your first token, right? I'm going to start my answer with this word, and that gives you the starting point in this space. And then each additional word will increase the fitness of your candidate solution up to that point. And then by adding more and more words in the local search term, by adding more and more steps, you will increase your fitness until you think, okay, I am done. Then that's like climbing a hill. Does that make sense? So think of any answer given by a language model as step-by-step construction, starting from a random point adding more and more steps, more and more words until you reach certain location in the entire space, and then with that you get the fitness of the generated solution as well.
How are you guiding, how are you telling it which way is up?
Oh, that's the probability distribution learned by the language.
Ah, okay.
Plus the context, yes.
Like to reach the question, how does the transformer know it reaches the end of the answer?
Oh, that's also a very good question. But I think in the training, it uses a explicit end of sentence token. So it understands when typically a sentence and a paragraph, for example, finishes. And then I think it follows the same thing. But yeah, how to carry that elements over to this analogy? That's a good question. I don't know how yet. But this was my feeble attempt to understand the arguments by the original paper in the language that I understand. So for the problems for which the self-consistency work, I think they are actually probably the easier problems in the problem space, in the sense that I'm rewording the original reason why it works with my search term. The terminology from the SPSE and the business landscape analysis. So I assume there is a fullest hill which has also the largest space, meaning you can start from different locations and then you will be sucked into this large hill and then you will climb that. Whereas there are smaller hills, so lower fitness level incorrect solutions. They have smaller base areas. So if you choose incorrectly your starting point, or some for small proportions, you are sort of sucked into that smaller hill, and then you can only climb that hill from that position. So I would argue that this would be one simpler landscape. Well, it is just an example of global local minima taken from internet, but as long as that highest hill is also the largest one, meaning the largest base area, then there are multiple ways to the top. Okay? Whereas the smaller hills, lower in height, but also smaller in the base area, and then you will find fewer ways to climb the incorrect hill. So if you do multiple climbs and then try to find the highest point in this landscape by taking the majority voting, then this condition, maybe self-consistency is the same as climbing those hills.
I have been reminded of it.
I'll run through the remaining slides. Okay, so that's self-consistency, and I promised I'm going to talk about execution. So I said, compared to natural language applications, software engineering has a unique position. On the top, I think what's going to happen with misuses of language model. You write some evil prompts, use a language model to generate some answers, which might be fake news, whatever. And then the only way to counter-argue that incorrect or malevolent outcome is basically to do the human check. Only humans can understand read the text and then decide this is not actually true. Whereas if it is programming language and natural language combined, the sort of dual channel proposed by Fred and Long. If that's the case, then we can actually have sort of different channel, which is the execution. It is a bit like human reading the text and then passing judgments about whether this is a correct argument or not. But we have lots of machinery to do that, thanks to the automated testing that we have worked on. So in the bug reproduction case, it was because we can execute the generated test cases that we could also cluster their output and then apply the self-consistency, right? Compared to, so maybe I should turn the story upside down. It will be very difficult to apply self-consistency if your task is to generate the most believable, what's the word, fake news. Because then, whether it is really, plausible fake news or not can be only decided by someone reading the article, and this person should be experts about the factual elements in the story, and then they decide, okay, this is plausible or not. And then also they need to decide what's the majority outcome is. For that, you need to establish identity relations between general language text, which is very difficult. But in the case of code, you execute something and then you can get definite concrete observation about the output, which allows us to group them and then apply the majority voting. I thought I was being careful with time. This is another very interesting example. Execution enabling the chains of thoughts. This is also under review, but it's the whole idea is entirely, I should credit someone who's sitting over there. We want to teach a language model to do what Andrea Zeller wrote in his book, Scientific Debugging. So do not just wish for any random code change to fix your bug. Instead, follow the scientific discovery framework. Hypothesize what's wrong about your code, and then predict its behavior based on your hypothesis, actually run the program, and then observe whether your hypothesis is supported or not. And then based on that, reiterate whether you have actually found the bug or you are still not understanding the root cause, therefore you need to come up with different hypotheses. So this was written for human developers to better debug your program, but in his experiment, he sort of patiently explains what the scientific debugging is to the language model, and then do this with zero shot, meaning we just tell you to follow the instruction. This is one example in human level benchmark. It's a function that checks whether a given integer n can be written as the sum of four positive even numbers. And then we need to check that the given number is also a even number and it is greater than or equal to 8. Because then it is 2 plus 2 plus 2 plus 2, and then from then we can add more even numbers. And currently it is buggy because it's not greater than or equal to 8, but it is greater than 8. Therefore, it fails the test where if we assert f8 is true, it fails because it says false. So if we give this program to this agent, it will first hypothesize about the wrong part. Maybe the input 8 is even, but the condition on line 5 is classifying it as odd. So it seemingly understood what the assertion is about. It has two parts, like the n being even and n greater than 8, and it is hypothesizing that the first half of that is incorrect. So based on that, it predicts, okay, if that's the case, then n mod 2 equals 0. The even check would be false, and then it runs the Python debugger. And from the observation, it was expecting that to be false, but it is actually true. Therefore, my hypothesis is incorrect and reject. Therefore, I'm going to establish the next hypothesis. The second part, n greater than or 8, n greater than 8 will be false. Runs another debugger experiment, and it is indeed false. Therefore, my hypothesis is supported. So maybe I now need to change that to n greater than or equal to 8. Then it will pass. That's the prediction. Run the experiments and nothing failed. So this time my hypothesis is supported and it declares that debugging is done. So that's what we try to argue as an explainable automation program with that, and it's one way of doing that. So again, going back to my earlier comparison between two, oh sorry, this is not that. we can do that because we can get the observation based on the concrete execution. If human has to intervene at each hypothesis, then that's really not helping to automate anything. So I'm nearly done, sorry. I was quite proud of that animation, but maybe not. So the latest thing that we are looking at is executability is good if the final outcome is code, but what if for example, we are crossing the barrier the other way around? One thing people are doing a lot is given a code, we want to automatically generate comments or documentation. And then documents cannot be executed, right? So right now, I think, again, this is, if the input is the code, give it to LLM, we generate documentation, and because it's a document, only humans can evaluate it, right? They either do that, or they just do very low-level lexical similarity metric and then claim that this is the good documentation. What we suggest is, what I for now name secondary execution. Suppose we start with a code, use an LLM to generate the documentation. Now I want to introduce another LLM. And now I want to tell the LLM, okay, this is the code, this is the documentation. Now generate something you can execute based on this document. And then we use that as if it's executable artifacts. Forget about the fact that the documents are also generated by LLM. Just to look at this test. And our argument is the better the documentation is, the more successful the generated test will be as well. Right? So this is still ongoing investigation, but we have some early evidence that. So y-axis is how many tests out of the generated one, and then on the x-axis we have different quality documentation. So if we tell a model to generate a test based on the target code and full documentation, then about slightly less than 80% of the generated tests will pass. If we only use the first sentence of the given documentation, then we have nothing to get the program behavior for, so the success rate goes down. If we do not give any comments, then it goes even further. And then if we give a long documentation, still something passes, but goes down. Right? So this is the human legal benchmark and the model was GPT. We also evaluated with smaller code model, code/language, natural language model, star coder, and then the pattern is the same. So maybe executability can be twice exploited if we get it again. Yeah. So maybe I talked too much just about large language models, but to this community, what does it mean? I think we need to rethink the semantic syntactic boundary. So GI and evolutionary computation in particular is about capturing the semantics with fitness function. So we need to spend a lot of time on that. And then everything else is mechanical sampling of the candidate solution space. So we just plug in any algorithm. That was our story. But maybe we can draw the big picture in different way. Second point, I think it is probably already over, but naively asking LLMs to solve my problem will not really go that far. And in the context of GI, again, I think we need to go beyond rewriting a few lines of code. So, we have tried, can you rewrite this method to be more faster? And then we can sometimes do that, but not so successfully. I think more interesting would be, doing more structural changes, like move the methods and rewrite entire class, etc. I think what we have learned from search optimization and ICSE GI in general will help us redraw the line between semantic and syntactic. And whatever we understand about dynamic analysis, will be very helpful to utilizing LLMs better because of the executability. But I still think that it is worthwhile to revisit this room because I think you don't have to be too easily persuaded into believing that they can think or they can infer. They are still essentially auto-completion engines, and therefore, whenever you want to reformulate your problem for LLMs, I think it is worthwhile to try this mental exercise. How can I look at this as if it is just text generation? What if I write a really good document or report solving this problem, then maybe that should be the format of your LLM application. So I introduced the Chinese room experiments because this is what the LLMs are. And I think they are interesting to us because of the syntax and semantic division and the ability to ignore that line, basically. And I have given you some examples of where I think LLMs can help us ignoring that line. Self-consistency is very useful thing if we want to make them more accurate and get high performance out of them. And I think our experience from search and materialistic optimization has something to give to us. I cannot quite wrap my head around them yet, but I am aware of some promising analogies. And I wanted to introduce the idea that as long as you can make something executable, even by applying one more random layer, which is another layer of LLM, maybe the executability itself is interesting enough and it's worth doing. Okay, that's it. Sorry about the time. Thank you. Thanks.
So, questions?
Yeah.
Dan?
Has anyone tried playing, so like the IE autocomplete with the static exact language, you're pretty good at narrowing down plenty of stuff. Can you combine that with the people combine that with an LLM, so it's got even more like refined path take generated code?
For example, at KAIST, one of my colleagues is what he's doing is combine the generative model with basically more grounded programming language filter. So you should not generate anything that's out of the grammar or anything that does not make any sense. So if we just want to refine the entire pipeline to be more precise and then more correct, then I think certainly there are ways to hybridize them. But at the same time, I think their capability comes out of the fact that we sort of ignore that and purely look at this as a really large corpus-based statistical model. So I'm not sure whether we can combine those two and then do the more accurate modeling and training at that scale. It would be interesting to see, but for practical reasons, I don't think that will be easy. And then it will be really interesting if you do that and actually the model performance goes down. I think that's also possible. Many of the power that we get out of these black boxes are attributable to the fact that we just do not care about totally being correct and then just feed more and more data. So
Just when you were talking about the telling it to give you no external dependencies, I play with GPT and I've had that. It just pulled, it's like, oh, just use this dependency. I don't want. I almost felt just one of us said, oh, but if I had an autocomplete, it could see what's already available. Maybe it would be more eager to not try and pull in random dependencies. Use what it's got.
Are you aware of the dependency attack that people came up with? So sometimes if you tell it to solve a programming task, it will make up a library, right? And then you write that library, but with malicious code and quickly release it, hoping that someone else will make the same query, and then the model will dream of the same non-existent library, but they will now find your version. And then therefore you can sneak in your code into someone else's system. So the chances are endless, I think. what's possible and what's not in both good and bad ways.